Math 1314, Spring 2022, Tyler Junior College. Section 4.3, Rational Equations. Video 3, Solving Rational Equations, Type 2. Before we jump into solving rational equations, what I have dubbed Type 2, let's quickly review what I meant by Type 1, shall we? By Type 1 equations, I meant rational equations whose denominators are monomials. In other words, whose denominators were single-term expressions such as x or 7 or 2x. We did go back and eventually determine restrictions, which is why it's up there in red. But the underlying principle behind all of these equations was they'd be better if they didn't have fractions. And so the strategy was to multiply by something capable of canceling the fractions. For example, in this equation, whose denominators were x, 7, and 2x, the number we multiplied by, or rather the term that we multiplied by, was 14x, because it gave us enough ammunition to cancel all the fractions when the time is right, multiply everything that was left over, and leave us a simpler equation. In this one, our denominators were x squared and x, and the least common denominator was x squared. Here they were just numerical, 5, 6, and 10. And the least common denominator was 30. You don't have to use the least common denominator, but it sure keeps things a little bit more manageable. And I recall that during the video, there was some things that were drawn and erased. They're just not captured in this PDF. So if all you're doing is looking at the PDFs of the whiteboards and not watching the videos, you are missing out on some of the action. But let's go back to Type 2. If Type 1 is denominators or monomials, what do you think Type 2 is? What do you think I'm calling Type 2? Well, denominators that aren't monomials, specifically denominators that have more than one term in them. Let's take a look at an example. Solve the rational equation. Check for extraneous solutions. And what do I mean by that? Well, do you remember when we were doing the previous equations and we determined the restrictions up front? Solutions that can't be solutions because they make a denominator equal to 0. This has something to do with that. Before we start solving this, a couple of things. Number one, I want to emphasize that I'm classifying this as a quote-unquote Type 2 rational equation. And just for full disclosure, that is my own description of it. I'm about to sneeze. Hold on. Glad I paused it in time. It was a rather loud sneeze. But I had kind of defined what a Type 1 equation was as a rational equation whose denominators were monomial single terms. And similarly, I'm kind of defining a Type 2 equation. Let me get this the way I want it formatted, red and a little bit larger font size. Type 2 is a rational equation. Rational equation. I need to learn to type. Let's widen this text box. With, well, for lack of a better word, non-monomial. It's a lot of N's and M's and O's terms. Why don't we just say with whose denominators have more than one term? Denominators have more than one term. So in other words, binomials are higher. Mono meaning 1, bi meaning 2, and of course have more than 2 terms. Now, the bad news is this is the thing. The good news is it really doesn't change our strategy at all, sort of. What do I mean by sort of? Well, when we were solving the ones in the previous video, and we'll go back and look at a few of them real quick, all we had to worry about is what was capable of canceling all the individual terms, like in the one you see on the screen. To cancel an x, a 7, and a 2x, it's really messy here, so it may be hard to see. To cancel an x, well, actually, I can go back to the original equation. To cancel an x, a 7, and a 2x, we found the least common denominator of 14x. And that's what we use to multiply across the equation to cancel everything. But the reason the canceling wasn't an issue is because there were no addition and subtraction problems in the denominator. Now, why is that an issue? Because the rule for canceling in a fraction is, has, and always will be the same. In a fraction, you can only cancel matching parts of multiplication problems. So if there's an addition or subtraction problem, that's an obstacle, and we got to figure out how to overcome it. And we're going to figure out how to overcome it right now. The strategy is still the same. Multiply by something to cancel the denominators, but I can only cancel parts of multiplication problems, not parts of addition or subtraction problems. For example, look at this middle fraction in this equation. Hold on. There we go. 2p over p plus 3. Is there anything you're tempted to cancel there? If you are tempted to cancel the p on the top with the p on the bottom, you'd be half right, but you'd also be half wrong, which therefore makes the whole move wrong. The p on the top is something you can cancel because it is part of a multiplication problem. And it has to be part of a multiplication problem because a fraction is a division problem. Multiplication and division are opposites. But the p on the bottom is not eligible to be canceled. It is not part of a multiplication problem. It is part of an addition problem. Addition and division are not opposites, therefore they don't cancel each other. So as tempting as it is, and I see this all the way through Calculus 3, as tempting as it is to say, I'm going to cross out these p's because they match, that's not enough. They also have to be parts of multiplication problems. All right. So we can't cross out the p on the bottom. We can't cross out the 3 either. So can we cross out anything? And the answer is actually yes, because here's the catch. When it comes to canceling an addition or subtraction problem, you cannot cancel a piece of it separately, but you can cancel it as a single large object. In other words, if there was a p plus 3 on top of the second fraction, then I could cancel it with the entire p plus 3 in the denominator. And what justifies that? Well, I could write p plus 3 as part of a multiplication problem. I could write it as 1 times p plus 3, showing that the entire binomial, the entire p plus 3, can be viewed as part of a multiplication problem and therefore can be canceled out in its entirety. If you want the short version of it, it's real simple. You can't cancel parts of an addition or subtraction problem in a fraction, but you can cancel the entire problem at once. So we're going to take the same approach. We're going to multiply to cancel all the denominators. Keep it in mind that we can only cancel parts of multiplication problems. Now, what about that first denominator, the one that says p squared minus 9? Guess what I would need to cancel it? I couldn't cancel its pieces, but I could cancel it as a whole. I could multiply by a p squared minus 9, and then that would set up a cancellation. However, if I do the same thing on the second fraction of p plus 3, then it's starting to look like I would have to multiply everything by not only p squared minus 9, but also p plus 3 to have enough ammunition throughout the entire equation to cancel all the denominators. That's going to make a big mess. There's a nice way around it, especially in problems that are designed to do this. A key strategy in solving rational equations type 2 with larger denominators is to factor their denominators completely. By definition, factoring turns something into a multiplication problem. I can cancel pieces of multiplication problems. So your big move on all of these right out the gate is to factor denominators completely. Let's widen that text box. And this will be our first move. It sets up multiplication problems in the denominators that we can therefore cancel with the right multiplication. All right, so let's move this to the next page and take it from the top. All right, the first thing I want to do is factor all the denominators. This is going to turn into a sequence of steps here in a moment. But by factoring denominators, I'll identify the factors that I need to cancel with some sort of multiplication. And needless to say, this does rely on factoring skills. So if your factoring skills are still not there, I strongly recommend going back and rewatching those factoring review videos and reaching out to me if you need some extra help. The binomial that I just put a box around, the p squared minus 9, that is a type of factoring problem. This is called a difference of squares. If I can get this to type. This is called a difference of squares, because both halves of the subtraction problem are squares. The one on the left is p squared, that's explicitly a square, but the one on the right is an implied square. 9 is 3 squared. And when you have something like p squared minus 3 squared, I'm going to take the time to actually put squares up there. I have to get out of the text box, shrink the font, and then redraw a text box up here where the squares would be. There we go. But if you have a difference of squares like p squared minus 3 squared, keep in mind the squares are on the p and the 3, then it'll factor into p minus 3 and p plus 3. It's a very convenient and quick factoring technique once you recognize that it's the difference of squares. So we're going to factor that denominator accordingly. We're going to factor it into p minus 3 and p plus 3. Now, why is that beneficial? I think it's pretty obvious. Well, maybe it's not so obvious. It's got two advantages to it. Number one, some of your fractions may have common factors in their denominator, meaning that whatever we need to cancel one of the fractions may help us cancel the other. And secondly, we still need to determine any restrictions. By factoring the denominators, we can look at each one individually and determine the restrictions that they invoke. For example, the first parentheses can't be 0, which means we automatically know that p cannot equal 3. Similarly, the second factor, the second parentheses, cannot equal 0, from which we can conclude that p cannot be negative 3. And by the time we get to the next fraction, you'll notice that it has the same factor of p plus 3 in the denominator, so it invokes the same restriction of p not equaling to negative 3, but we already had that in our list of things that p cannot equal. Get my name out of there, it just seems to float around sometimes. All right, so it is worth mentioning at the beginning of any rational equation that there are certain values that you cannot get for solutions, and if you get them, then you must throw them out. So our restrictions is that p cannot equal 3 or negative 3. I'm going to blow the font size up and then draw a slash through the equal sign so that it says not equal to. And I guess I'll widen the text box and draw the line through the equal sign. All right, so right away we get p that p can't be 3 or negative 3. So what happens at the end if we get one of these? Well, we'll cross that bridge when we come to it. Let's solve this guy. We're gonna do the same thing we did in the previous video. We're gonna multiply everything by something capable of canceling all the denominators. Now, there's an interesting duality between the size of a problem and how easy it is to see how to attack it. The duality is the bigger the pieces, the bigger the polynomials and denominators, the easier it is to see what you need to multiply by. For example, if I want to cancel the first fraction's denominators, I have to it only has one denominator. I have to multiply by both p plus 3 and p minus 3. Give me 1 second to move this over because I would like to write those on the left side of this fraction. I'll just grab and move. See if I can grab these guys. There we go. Looks like I lost part of it. That's okay. I can redraw. I'll just redraw the whole thing over here. All right. So anyway, if we're going to multiply to cancel the first fraction, we would have to multiply by both a p plus 3 and a p minus 3, because that will set up enough factors to cancel the entire denominator in that fraction. But whatever we multiply in one part of the equation, we got to multiply to all the terms. So just because the first fraction needs both of those parentheses, that means that every term, the second fraction, and even the 1 at the end, it's not a fraction, but as part of this equation, it gets sucked up in all the multiplication on both sides. But we're going to multiply all three parts of this equation by p plus 3 and p minus 3, because that is sufficient to cancel the first fraction's denominator. And, as luck would have it, or it's not so lucky, it's also sufficient to cancel that fraction's denominator, because that fraction's denominator has only a p plus 3 as a factor, and we just hit it with a p plus 3. So all the fractions denominators are canceled, and now we need to gather up what's left over. In the first fraction, the only thing that's left is 36. But on the second fraction, we've got a couple of things left. We've got this 2p, and we've also got this p minus 3 that we multiplied by, but didn't cancel. We had to multiply it because of the first fraction, we have to multiply the same thing on both sides. So that p minus 3 did not get canceled, and therefore is still there with the 2p in front of it. And then on the other side of the subtraction sign, we didn't cancel anything. There were no fractions. I don't really need the 1 anymore, but I'm going to leave it there because in any other problem, if it were any other number, it would still be there. So let's do it always works and leave the 1 there, because that'll always work with any number. But if we erased it, then we might do that when it's not 1. All right, so no more fractions. I'm not out of the woods yet, not by far. I've got all this down here. Let's move this over to the next page and see where we should go from there. Now that we've fixed one issue, the fractions, we have to fix another issue, the parentheses. But by now you should know how to get rid of most parentheses when they're being multiplied. In the first term on the right, the 2p times p minus 3, I'm not too worried about that. That's going to be the distributive property. We'll get to that in a second. But the second term, and notice that I included the minus with the 1, because if that 1 gets distributed, then the minus goes with it. But in that next term, we have a combo problem, if you will. We have what looks like a distributive property problem because of this -1 waiting to get distributed. But it also looks like we got this FOIL problem because of the 2 binomials. So which is it? Actually, it's both. So which do we do first? Technically, it doesn't matter which one you do first as long as you do it carefully. I found in the past that students who do the distributive property first tend to mess this up. So I would advocate when you have both a distributive property setup and a FOIL setup, I would recommend doing the FOIL first and saving the distribution for later. We're going to FOIL this out, except we're not going to, because I already know what it equals. And if you remember where that came from, you know what it equals to. Okay, of course it's gone. But remember when we took this guy and said it was a difference of squares and it factored into p minus 3 and p plus 3? Well, that's exactly what we have there. That is the factored version of p squared minus 9. So we should get that back. And then we're going to distribute the -1. So let's go ahead and do that. We'll get -1 p squared. And then -1 times -9 is +9. And we might as well go ahead and distribute over here as well. Carefully. 2p times p is 2p squared. And 2p times -3 is -6p. All right, obstacle overcome. The parentheses are gone. And notice that we have a quadratic equation. So we're probably going to want to get it equal to 0. But first, notice that there's like terms on the right side. There is a 2p squared and there is a minus p squared. So I am going to combine those, but let's multitask. It's not a bad idea to learn to multitask. Sometimes you can knock out 2 moves in one line. If I'm going to get this equal to 0, I'm probably going to subtract the 36 from both sides also. I say probably because it's not the only way to get a 0 on one side of this equation, but I'm choosing to get the 0 on the left side because I'm looking about a step or 2 ahead. I want to keep my p squareds positive. Makes it life easier. And when I combine my p squareds, they're going to end up positive as long as they stay on the right side. So for those reasons, I would 0 out the left side by subtracting 36 from both sides. Combine the p squared terms that are currently in green boxes. 2p squared minus p squared is p squared. And more specifically, 2p squared minus 1p squared is 1p squared. But I don't have to write that 1. Minus 6p. And then when I add the +9 and the -36, I get -27. This problem doesn't seem to know when to quit. Every time I fix one problem, I get another. I fix the fractions, I got parentheses. I fix the parentheses, I get a p squared. But now it's at a point where we can send it home because this is just a quadratic equation. You want to know why we spent 3 homeworks solving quadratic equations? Because there's a lot of ways to do them and they show up all the time. So let's move this to the next page and finish this guy. You are more than welcome to get out the quadratic formula, but you have several techniques for solving quadratic equations, one of which is solving by factoring. If your factoring skills are honed, you should ask yourself if I can factor this, if I can turn it back into a FOIL problem, that would give me p squared minus 6p minus 27. Well, without reteaching all of the factoring moves, when you're factoring a trinomial whose leading coefficient is 1, it boils down to finding 2 numbers that have a sum of the coefficient in the middle, so a sum of -6, and a product of the constant term, a product of negative 27. And if you can find those two numbers, you can get this guy factored quickly. Do you know what they are? They are p minus 9 and p plus 3. When I add them, I get negative 6. When I multiply them, I get negative 27. Now, this is exactly where we want it. It's factored on one side, 0 on the other. And the zero product principle, or did I call it the zero factor principle? It has a lot of very similar names. Anyway, we can split this. P minus 9 is equal to 0. P plus 3 is equal to 0. Because the only way a multiplication problem can equal 0 is if at least one of its factors is 0. This gives us solutions of p equals 9 and p equals negative 3. And we finally breathe a sigh of relief because our goal is achieved. We got the p by itself. We can relax. Or can we? Oh my gosh, this man never shuts up. This type of problem, rational equation, has a built-in issue. We've already discussed it. We got to go back a few pages to see it. Well, it's right here. But remember at the very beginning, before we solved anything, we identified that there were two restrictions on this equation solutions. P can't be 3 and P can't be negative 3 because both of those numbers make denominators equal to 0. Specifically, if I put 3 here, I'll get 0. And if I put negative 3 here or here, I will also get 0. So keeping in mind that we had restrictions, we can't get 3 or negative 3 for an answer. Well, guess what? We just got negative 3 for an answer. We didn't do anything wrong. This happens sometimes with this type of equation. The reason why it happens is kind of stealthy. I'll explain it just briefly. Every move that we did preserves the equality of this equation, meaning if I do something like subtract 36 from both sides like I did here and here, if my equation is true, subtracting 36 from both sides will keep it true. Or multiplying both sides by a number, or dividing, or all the moves that we do on both sides to change the looks of an equation, most of the time preserves the truth value of an equation, meaning that it can take something that's true and keep it true, or take something that's false and keep it false. But we did a move that violates that. And it was a move that we had to do. But when we multiplied, and this is a very, very stealthy thing that a lot of people don't ever stop to think about, but when we multiplied both sides of the equation by p plus 3 and p minus 3, this can take something that is false and make it appear to be true. And the reason is, when you multiply by a variable, that variable could possibly turn something into 0. In other words, when I multiply by p plus 3 and p minus 3, I don't know what those equal. They could equal 0. And if p equals negative 3, they all would equal to 0. And why is that a problem? Well, because multiplying an equation on both sides by 0 can take something that's false and make it true. To show you a real quick example without dwelling on it too long, because I've already dwelt on it too long. If I said 7 equals 5, that is clearly false. Nobody's going to argue that that's true. But if I multiply both sides by 0, it makes it true. Multiplying an equation on both sides by 0 does not always preserve its truth value. In fact, it can botch it up. So that's why this answer snuck in. This answer snuck in because we took a true equation, multiplied it both sides by something that could be 0 and turned it into a false equation, or a potentially false equation, I should say. That's why the negative 3 snuck in, because we didn't accidentally, we did a move out of necessity, multiplying both sides of the equation by all those parentheses. We did something that could possibly let in a bad answer. And that's why we have to check for domain restrictions. And that's why this problem said, check for extraneous solutions. The phrase extraneous solution basically means a solution that you get that isn't a solution. Negative 3 is not a solution. It will not make this equation true. Let me try that again. Negative 3 will not make that equation true. It makes both sides undefined. Now, negative 3 will make this equation true, but that equation resulted from doing a move that could turn something true into false or vice versa. So I guess the moral of the story is when you're solving a rational equation, be very careful at the end to spot check your solutions and make sure that no extraneous solutions snuck in. So what do we do at this point? Well, we kind of make the following comment. Since p equals -3 is restricted from being a solution, the only solution is p equals 9. And the online homework will know this. If you try to type in -3 and 9 for this problem, it would say that it's wrong. Fix something here. Hold on. There we go. The -3 is called extraneous. So any problem that says check for extraneous solutions means you may do a move that allows in an answer that is not an answer. You got to catch it and throw it away. So the only solution is 9. We're going to take a look at one more because I really don't think a bunch of these is going to make them any clearer. And then we're going to turn it into an algorithm, step 1, step 2, step 3. Solve. Check for extraneous solutions. 2 over x plus 5 plus 2 over x squared plus 9x plus 20 equals 4x over x plus 4. Looks intimidating, I know. But at the beginning, there are 2 things we need to do. First, we need to factor any denominator we can. Second, we need to identify determine any restrictions. So let's start by factoring the second denominator. Now, I'll tell you a little secret about some of these types of problems in most algebra books. A lot of these problems that have a quadratic denominator like this one, and a pair of linear denominators like x plus 5 and x plus 4, a lot of these problems are designed to have common factors and denominators. And therefore, when you factor, you can expect some of the other denominators to appear. That's not guaranteed, but I've seen enough of these to know that this is a very common setup. Can you think of 2 factors for x squared plus 9x plus 20? Hint, we would need 2 numbers that add to give 9 and multiply to give 20. Well, that would be plus 5 and plus 4. I'm not going to write it there. I'm going to leave the original equation intact, but I'm going to say answer. And first, we're going to factor our denominators. And this will morph into a how-to list. First, factor all denominators. Now, some of them may not require factoring. Your linear factors like x plus 5 and x plus 4, whose highest power is 1. If those factor at all, it's only because they have a greatest common factor, which these do not. All right, so we're going to factor the second denominator. First fraction is going to stay the same, 2 over x plus 5. The second denominator will factor in x plus 5 times x plus 4. Again, if your factoring skills need brushing up, I implore you to go watch the factoring review videos from an earlier homework assignment. The third fraction on the right side of the equal sign only has a linear denominator, x plus 4. There's no greatest common factor to factor out of it. But that's okay, because looking across all 3 fractions, there's only 2 factors, x plus 5 and x plus 4. So our next move is to identify any restrictions, or rather determine any restrictions. This is easy once the denominators are factored, because you just have to go one denominator's factor at a time, one factor at a time, and ask yourself, what would x equal that turns this into 0? For example, for x plus 5, x equals -5 would make that 0. So one of my restrictions is x cannot equal -5. On the second fractions denominator, we have an x plus 5 and an x plus 4. We've already dealt with the x plus 5, but the x plus 4 can't be 0 either, meaning that x cannot be -4. X cannot equal -4. And by the time we get to the third and final fraction, its denominator is x plus 4, but we've already identified the restriction that it would invoke. So keep it in mind that at the end, if we get -5 or -4, we have to throw it out. Now, by the way, I've seen problems where we don't throw out anything, and I've seen problems where we throw out everything. And if that happens, there's no solution. So you can never assume up front, oh, I'm going to throw out exactly one solution. There's only going to be one extraneous solution or something like that, because there's no guarantee. So you have to check them all at the end. All right, so what do we do next? Well, now it's time to actually start solving this. So for our next move, we're going to multiply both sides of the equation by the least common denominator. Now, technically, it doesn't have to be the least common denominator. It just has to be something capable of canceling every single denominator. You would want to use the least common denominator because if you use more than necessary, then what you're left with afterwards might be difficult, if not impossible, to solve. So you don't want to fix one problem of killing the fractions by multiplying by something large enough to do it and create another problem by being left with a problem that's too large to handle. Here's what I mean. What some people will do is just grab all three denominators and fuse them together. I'll take an x plus 5, an x plus 5, and an x plus 4, and another x plus 4, and make one big chunky common denominator and multiply everything by that. Yeah, do that and watch what kind of mess you'll make afterwards. You don't want to use too much to take out these fractions. Here, I think it's obvious we just need to multiply by x plus 5 and x plus 4. But if it wasn't, watch this. Set them up one at a time. To cancel the first fraction's denominator, I need an x plus 5. But if I give him an x plus 5, everybody gets an x plus 5, whether or not they need it. First fraction set up. Go to the second fraction. To cancel it, I need an x plus 5 and an x plus 4. I've already given it an x plus 5, but now I need to give it an x plus 4. And I don't normally recommend writing your factors on top of each other like that. But, when space dictates otherwise, you can stack them on top of each other. But everybody gets an x plus 4 just because the middle fraction needed it. And by the time we get to the last fraction, it needs an x plus 4 to cancel its denominator, and it already has one. So you're going to multiply both sides of the equation by the least common denominator so that you can cancel all fractions and gather what's left. Because on most of the fractions, you'll cancel something but not everything. And you have to gather whatever is left over. For example, on the first fraction, I'm going to cancel the x, I'm going to cancel the x plus 5s. That's going to leave a 2 times an x plus 4. So let's go ahead and go to the next page and start building what our equation looks like. The first fraction will be left with 2 times x plus 4. All right. Let's go to the second fraction. Well, that one's a little bit easier because the x plus 5s cancel, as do the x plus 4s, leaving only a 2, a plus 2 to be specific. So plus 2 equals. And on the right side of the equation, the x plus 4s cancel, leaving us a 4 and an x plus 5. A 4, something's not right. I lost something. Did you catch it? Look at the third fraction here. Now look at it. Well, it's okay on the top, but on the bottom, I left off the x. I'm glad I caught that. And the only reason I caught that is because I designed this problem to do something. And in the end, it had an x up there. So yeah, there should have been we'll go back one more. There should have been an x on that 4. And in the third fraction, we're left with a 4x and an x plus 5 that we multiplied by but didn't cancel. So 4x times x plus 5. So it's quite the bit of setup, but the problem is clearly better now than it was before. Instead of having 3 fractions, it has none. At this point, you should no longer have a rational equation, and your next move is to finish solving. Now, finish solving may invoke something different depending upon the type of equation that you have. Right now, there's parentheses that need to be dealt with. I can fix that by distributing. On the first parentheses, I'll get 2x plus 4, and there's still a plus 2 there, equals. And on the right side, I'm going to get 4x squared plus 20x, I believe. Is that right? Yeah, that looks right, except something's not adding up here. Found it. I misdistributed the very first parentheses. 2 times x is 2x. I'm not arguing with that. But 2 times 4 is 8. It doesn't bother me to make mistakes. I know I'm the teacher, because there's a good lesson to be learned. It doesn't matter how good you are, how good you think you are, how many degrees in math you may have. If you're careless, you will make the most simplest of mistakes. Let's continue. We do have like terms on the left, so let's go ahead and put them together. 2x plus 10 because of the 8 plus 2. But now we have a quadratic equation. Surprise, surprise. So we need to get it equal to 0. Whenever you get a quadratic equation equal to 0, you should let the following motivate your decision. Keep the x squared positive. My x squared on the right is positive. I don't want to move it. It's going to stay on the right, meaning that everything will wind up on the right, which means we need to empty out the left. The moves that I'm doing right now to empty out the left should be pretty obvious by now. Subtract to get rid of anything that's added. Add to get rid of anything that's subtracted. Everything cancels out, leaves a 0. And on the right side, we have 4x squared plus 18x minus 10. So now it's a quadratic equation ready to succumb to whatever technique we're going to use to solve it. 0 equals 4x squared plus 18x minus 10. Now, if you're a quadratic formula person, get it out, break out 2 solutions, and you'll get there. I like factoring. Speaking of which, notice something about all 4 of the numbers, all 3 of the coefficients in this trinomial. They're all even, which makes them all multiples of 2, which means they have at least a common factor of 2. And if I'm going to be factoring, taking out a common factor is not a bad idea. 2 can be undistributed to leave 2x squared plus 9x minus 5. At that point, I now have a quadratic, meaning highest power is 2, trinomial, 3 terms inside the parentheses. And I could hit that with the quadratic formula. But if I was going to use quadratic formula, I would have used it a line earlier. I'm going to still try to factor this. For the sake of time, because I know this video is going on a little bit longer than I wanted to, I'm not going to get into how to factor this. But I'm pretty sure that 2x squared plus 9x minus 5 factors into 2x minus 1 and x plus 5. A real quick check of FOIL. There's 2x squared. There's 10x minus 1x, which is 9x. And there's negative 5. A real quick FOIL shows that it is the correct answer. And if you're wondering how I insta-factor like that, I've done this so long, I know what I'm looking for when I build this FOIL problem. Specifically, I'm trying to make sure that these guys in the middle make the plus 9x. The 2x squared up front, the minus 5 on the end, that's easy to see. It's building that middle term. That takes some practice. But I digress. Look where we are. We're 0 on one side, factored on the other. And when that happens, that means one of the factors is 0. So either x plus 5 is equal to 0, or 2x minus 1 is equal to 0. Now this 2 in front is a factor. It's part of a multiplication problem. And technically, you could put it equal to 0. But there are 2 problems with me writing that. Number 1, it's clearly not true. And number 2, the whole reason I'm splitting this is to separate the x's from each other so I can solve for them individually. But 2 by itself contains no x to solve for. So there's really no reason to write 2 is equal to 0. Now, if you want to, and if you're still worried about me just ignoring that 2, then consider this. What if before making this split move, I decided to divide both sides of this equation by 2? I didn't. But what if I said I'm going to divide both sides by 2? Then the 2's would cancel, but 0 divided by 2 would still be 0. I would have 0 equals those 2 parentheses. So I can justify ignoring the 2 because I could divide both sides by it and make it disappear anyway. But it doesn't have an x to solve for, so there's no reason for me to try to mess with it any further. My 2 solutions are, oops, let me take the line thickness down. My 2 solutions are x equals 1/2. I'm going to assume you can solve 2x minus 1 equals 0, and x equals negative 5. So it was quite the journey. But a lot of these rational equations are, because they often turn into quadratic equations because we have to do some multiplying to cancel stuff. Multiplying creates powers, but at least we're done. Or are we? Remember the restrictions? Can't be -5, can't be -4. Uh-oh. X equals -5. That is extraneous. What does that mean? It means it's not a solution. It's a solution of the equation after we clear the fractions, but it's not a solution of the equation beforehand. So as an extraneous solution, it gets removed. And so the only answer is x equals 1/2. Only solution. That's supposed to be red. X equals 1/2. Let's put that back in red. Red's usually like warning, but in this case, it's the answer. Okay, so yeah, they're messy. I'm not going to lie. But keep in mind that I'm not teaching this class to you because I'm trying to teach you a skill that you're going to use to go get a job. You might need this to go to a future math class where you might learn job-oriented skills there. And don't get me wrong, I could come up with some jobs that solve rational equations as part of their skill sets. Usually those are like STEM jobs, engineering jobs, or whatnot. So why are you doing this? Because as I said from day one, and I will say over and over again, I'm trying to teach this class, use this class as a tool for teaching problem-solving skills, identifying obstacles that are in the way, making measures to overcome those obstacles until you've reached your final goal. So let's just recap real quick what happened to remind you that this was a problem-solving exercise. Our goal, when it says solve, is the bottom line here, x equals what? And there was a lot of stuff in the way. The fractions were in the way. Fractions are division problems. We can undo dividing by multiplying. We did that, and in the midst of that, we had to factor to find the things to cancel. Fractions are gone. Now the parentheses were in the way. We have tools for getting rid of those. Distributing, foiling, the most common ones. That created a quadratic equation. That's an issue in its own right, but the standard strategy is get it equal to 0 and either break out the quadratic formula or hit it with factoring. But every time we fixed one thing, we identified the next obstacle and had a plan to overcome it until we got to the end. So if you can at least embed that problem-solving protocol in your mind, then it's going to help you outside of this class. All right, I think it's time to end this video.